Okay, so today is the start of your module 3. Okay. I'm gonna make announcements at the end of our lecture, so please stay tuned. Try to listen until the end. Okay. Regarding your module 2 grades. But for now, we'll just continue our lecture. So in your syllabus, thermal stress should be in module 2, but because of our foundation week, I moved it to module 3. So now let's try to finish thermal stress today. Okay, so let's dive right in. Introduction. All right. So thermal strain, denoted by epsilon sub T, is just strain caused by changes in temperature. So this goes along with our topic strain from module 2. So the equation for that is just alpha AT, where alpha is the coefficient of thermal expansion and change in T rather than AT is change in temperature. Then due to strain, okay, caused by deformation, so the equation for deformation denoted by delta T equals alpha L change in T. Okay? So when you have a deformation due to a change in temperature, obviously you're going to have thermal stress as well. And thermal stress is caused by internal forces when the deformation of a body is restricted. So originally, if you have a free moving body and it changes in temperature, all it has is deformation. But if you restrict that movement, okay, you're gonna have what we call your thermal stress. So let's talk about the process in solving for problems involving thermal stresses or thermal strain. So first, you relax the supports. So that means you remove the constraints that prevent the thermal deformation to occur freely. Later on in the examples, I'll show you what that means. After relaxing the supports, draw a sketch that exaggerates the magnitude of deformations once your body is free to expand or contract, and then derive compatibility equations. Remember, compatibility equations are just equations where you relate measurements to one another. Okay, so usually geometry or geometrical equations. Next, apply the forces that are necessary to restore the specified conditions of constraint. Then add the deformations caused by these forces to the sketch that was drawn previously. So basically, you're just returning your sketch, your free moving body, to its constrained state by using forces. Okay. And then lastly, write the relationship between the thermal deformation and the deformation due to constraint forces. So again, in short, remove the constraints, allow your body to expand or contract, create an equation out of that expansion. Next, add forces that would return your body to its constraint form. And then relate the deformation due to thermal change and deformation due to the force applied. Okay. So let's have an example to show you what that means. Okay, examples. Number 1. A steel rod with a cross-sectional area of 0.25 inch squared is stretched between two fixed points. The tensile load at 70 degrees Fahrenheit is 1,200 pounds. What will be the stress at 0 degrees Fahrenheit? At what temperature will the stress be 0? And then assume alpha, your coefficient of expansion, to be 6.5 times 10 raised to negative 6 inches per inch degree Fahrenheit, or just 6.5 times 10 raised to negative 6 per degree Fahrenheit. Okay. That's another way to write that. And then your E, modulus of elasticity, is just 29 times 10 raised to 6 psi. Okay. So for this topic, I've actually already written out all your solutions. Okay. So just follow along. So number 1, write first the given. So area 0.25, as you can see, initial temperature, yeah, tensile load at 70, so that's your initial temp, T sub O. Then tensile load 1,200 pounds, coefficient of expansion, then your E. Then letter A, what will be the stress if you reduce the temperature to 0 degrees Fahrenheit. Okay, so let's sketch that. So initially, this is what your rod looks like, right? Steel rod. Then it's stretched to this end, yeah? Stretched between two fixed points. So these are your fixed points. Okay? So again, original form stretched up to this end. Now, this length is the deformation due to a load or your tensile load. That's why I denoted it as delta P for deformation due to load. So all of that are at 70 degrees. Next, okay, afterwards, what happens if your original your original steel rod is cooled to 0 degrees? So remember, increase in temperature, your object will expand. Decrease in temperature, your object will contract. And obviously, from 70 to 0, that's a decrease in temperature, your object will contract. So from your original position, it's going to contract this way. So this is now your change in T. Okay? So that's your deformation due to change in temperature. Now that you have your sketch, create your compatibility equation. So compatibility equation, if you've noticed, it's like this. So this is your deformation due to force, deformation due to temperature. Therefore, you can say this is the total deformation of your object, right? So writing that in equation form, sigma, the total deformation of your object, is equal to sigma t, not sigma, delta is equal to delta t plus delta p. Right? And then just write all of that in its equation form. So delta, since we're looking for total stress experience due to force and temperature, remember the equation for deformation is PL over AE. That's the basic equation. Or P over A is just stress, so this is stress L over E. So let's use this to denote the total deformation. That's why this is stress L over E, denoting total stress experience. So equals equation for change in temperature is just alpha L change in T. Then obviously for force, it's your usual PL over E. Then just plug in your values. So sigma, that's what we're looking for. E is 29 times 10 raised to 6 given PSI. Next, alpha, per degree Fahrenheit, so no problem there. Okay. Next, temperature. Since this is degree Fahrenheit, your temperature should also be in Fahrenheit, which it is, so no need to convert. So change in T is just final minus initial. Final temperature was when you cooled down to 0, so 0 minus initial 70. Then plus PL over AE. P is the force that made this expand or stretch to this end. So that's your 1,200 over AE. And if you've noticed, L cancels out. That's why there's no L here, right? L cancels out. And over AE, A is given inch squared, PSI, which is pounds per square inch. So again, uniform units, no need to convert. So 0.25, again, E is 29 times 10 raised to 6. Solving for sigma, you get 17995 PSI. Next, letter B. At what temperature will the stress be 0? So now I want my stress to be 0. Your stress is 0, okay, when it's not experiencing any internal pressure or internal force. And when will that happen? So, again, this is the original position of your steel rod. It's stretched to this position. At what temperature will the stress here be 0? Because obviously, because it's stretched, there's a stress being experienced by your steel rod. Now again, for it to be 0, okay, the change in temperature or the stress due to change in temperature should equate stress being done here. So for example, what if I increase the temperature of this rod? So your rod now from this position will naturally expand. Okay? So if it naturally expands up to this point, right? Therefore, I don't need to stretch it anymore. The force being applied by this 1,200 pounds is void, meaning it doesn't create an effect. Because this force is enough only to get this end up to this end, right? So if I increase temperature and your rod expands by itself, so there's no need for your force, okay? And since you're just expanding it for this side to touch this side, right? The expansion is not constrained. Therefore, there's no thermal stress. Okay? Again, expand your rod up to this end. Okay? Just touching this end. Therefore, your expansion is not constrained. Your rod is free to move from this point to this point. Therefore, there's no thermal stress. And since my rod is touching this end because of expansion, okay, I don't need this force anymore. Hence, stress due to force is also zero. So now I need to know up to what temperature should I heat this up so that stress is zero. So in drawing that, this is what that looks like. Okay. So this is stress due to force. I need to match that. This is deformation due to force. I need to match that with deformation due to temperature. So in equation, that's just delta T equals delta T. Okay? And again, the explanation for that was given earlier. So plug in your equation, alpha L change in T equals PL over AE, sub in your values. We're looking for final temp, so that's your TF, minus your initial temp, which is 70, equals P over AE. And again, L cancels out. That's why there's no L here. And solving for TF, you get 95.46. Okay? So that's number one. Do you have any questions? Okay, none? So do you understand? Please answer yes or no. Okay, great. Let's move on to number two. A steel railroad rails. Steel railroad rails, 10 meters long, are laid with a clearance of 3 millimeters at a temperature of 15 degrees Celsius. So obviously, 15 is your initial temp. At what temperature will the rails just touch? Next, what stress would be induced in the rails at that temperature if there were no initial clearance? And assume your alpha is 11.77 micrometers per meter degrees Celsius, and E is 200 GPa. Okay, so again, let's write out our given. Your clearance is 3. You have steel railroad tracks, 10 meters long, initial temp 15. Then let's focus on the question, at what temperature will your rails touch? So it looks like this. So write your given, initial temp, alpha E. So this is your steel railroad tracks or rails, right? For it to expand, for it to touch, it needs to expand, which means you need an increase in temperature. So when you increase the temperature, okay, your object will expand 3 ways. One is linearly, meaning in a line, in one direction. Next is by area, next is by volume. So we're only focusing on linear expansion for these types of problems. So therefore, when you have linear expansion, if there's no constraint, your object will expand in both sides, obviously. Here, there's a constraint here. That's why it didn't expand this way, only this way, all right? Here, there's no constraint. So your railroad, your rails, will expand this way and then this way. Okay? And therefore, if you write it out, this is your total deformation due to temperature over 2. Since it's gonna expand in each direction in the same amount. Okay, so therefore, deformation is distributed equally. So over 2 over 2. Okay, and we just want to bridge the gap, and that gap is 3 millimeters. So this is gonna expand this way. Obviously, this rail will also expand this way. So they're gonna expand equally. Therefore, this side will expand half of this total length, which is 1.5. Okay, but this side as well is gonna expand that way, which is again 1.5. This is just 1.5. So in total, if this side is gonna expand 1.5, this side is gonna expand 1.5, the total deformation due to temperature of your track or your rail is 3 millimeters. So writing that out in equation form, deformation due to temp is 3. Now what if this is constrained on one side? Let's say here, okay? It's constrained here for some reason. Therefore, okay, if this is gonna touch, the only way this rail will deform is this way. So this now becomes just deformation due to temperature. Okay? And it's still gonna deform this amount because again, this is also gonna deform, expand by this amount. So instead of equals 3, this is equal to gap, half of the gap, which is 1.5. Okay? So that will happen if your one side is constrained. But it's not, so it's equal to 3. There. And then just write your temperature. Just write your equation. Alpha L change in T equals 3. So everything in millimeters. Okay, you need to make sure your uniforms, your units are uniform. Okay, so first alpha. Alpha is 117 micrometer per meter degree Celsius. I need everything in millimeter. So first, I need to convert micrometer to meter so that that cancels out. Similar here, this was inch per inch degree Fahrenheit, so I just didn't include inches. So same here. So convert. So 117 micrometer per meter. Multiply it by conversion factor. So 1 micrometer is just 1 times 10 raised to negative 6 meters. Okay, so remember that conversion. Therefore, micrometer cancels out, right? And then meter also cancels out. So this is in essential 117, or in essence 117 times 10 raised to negative 6 per degree Celsius only. Okay, so that's done. Times L. RL is the length of your object, which is 10 meters. Again, everything in millimeters, because our deformation is in millimeters. I just want everything in uniform units. So convert meters to millimeters. So obviously 1 meter is 1,000 millimeters. Okay. So that's the conversion. Then change in temperature, it's in degrees Celsius, so no problem there. So again, all of this means 117 times 10 raised to negative 6 times 10 times 1,000, converting this to millimeters, right? Then times change in temperature, which is final temp minus initial 15, that equals 3. And then solving for TF, you get 40.64 degrees Celsius. So that's it. Next, second part, what stress would be induced at that temperature at 46 degrees, at 40 degrees, if there were no clearance. So meaning your rails are already touching. Okay, so let's say, yan. Now you have this constraint. There's also a track here. Okay? And obviously also on this side. So what's gonna happen? So first of all, due to temperature, it's gonna deform this way still on both sides. Okay? Because remember the first step, free your constraints. So I remove the constraint, let this expand. It's gonna expand this way as explained earlier. So delta T over 2, delta T over 2. Next, put back or apply forces that will put it back to its constrained form. So meaning, I need to add force here and here so that this end will go back to this end. Okay? And because of that force, your track or your rail will experience another change or deformation due to force. So it's equal to this, right? Your force is just gonna put this back to this side. So now I denote that as delta P for deformation due to force. Okay? So therefore, actually it's over 2. Okay? These force are equal, so they're gonna deform each side of the same material equally as well. So that's why it's still over 2 over 2. So in short, delta T over 2 equals delta P over 2. So delta T equals delta P. So now you have that equation. That's your compatibility equation. And then we're looking for stress. So the equation that I'll use for deformation due to force is not PL over AE, it's just sigma L over E. Okay, again, sigma is just P over E. That's why it turned into sigma L over E. Then equals alpha L change in P. Plug in your values. E is, as you can see, L cancels out again. So sigma over 200 times 10 raised to 3. GPA, convert to MPA, right? That's 200 times 10 raised to 3 MPA. That's Newton per millimeter squared. Remember, our deformation was in millimeter. That's why I convert this to MPA, like our previous lectures. So 200 times 10 raised to 3 equals alpha. Again, that's 117 times 10 raised to negative 6. Change in T. So that's TF, our temperature that we solved for, 40.64 minus initial temp, which was given 15. Then solve for sigma, you get 60 MPa. Okay? So the only problem with thermal deformation is knowing what's going to happen with your object and how to write your compatibility equations. Okay. Any questions for number 2? None, do you understand number 2? Please answer yes or no. Right, good. Next, let's move on to number 3. Okay. Calculate the increase in stress for each segment of the compound bar shown in the figure if the temperature increases by 100 degrees Fahrenheit. Assume that the supports are unyielding and that the bar is suitably braced against buckling. So buckling is another deformation that would happen for these types of system usually. But since it states there that it's braced against buckling, so we're not going to include that anymore. Okay? Supports are unyielding, meaning this won't budge. It's going to stay as is. So again, let's see. We're going to calculate stress for each segment, your aluminum and steel bar. Okay? If we increase temp by 100. Right, so let's go back to our solution. Okay, so you have your figure, right? There's gonna be an increase in temperature. So again, just reminding you the procedure. Let's look at that again. Step 1, relax supports. Step 2, sketch. Step 3, add forces. Then write sketch, compatibility equation, forces, the relationship between deformations. Right. So compatibility equation and equation due to deformations kind of blend in anyway. So again, let's go back. Relax the supports. So I'm going to remove that, your fixed end supports. Or no, not fixed end, but your bracings. Remove that. Meaning, when you remove that, your bar will expand freely. There's still, what do you call this? Bracing there, or rather constraint there, since they're joined at this end. So your object, you can just draw it this way. Your aluminum bar will expand this way due to change in increase in temperature. And then your steel bar will elongate this way, again due to change in temperature. Okay, after sketching how your material will behave, add in your force to put it back to its original position. So to put it back, write your P, same amount, so that it goes back to this. Then, therefore, your bar again will experience another change in length or deformation due to force. So therefore, this is deformation due to temperature in aluminum. This is deformation due to force of aluminum. And same thing with your steel bar. And after you have that, write your compatibility equation. So, if we add the expansion of your bar, okay, and since all of this will return to its original position, that expansion is equal to the contraction due to force. Okay. So writing your equation, you have deformation due to force equals deformation due to temperature. Okay? So that's one way to write that. Since everything goes back to normal, the expansion equals the contraction. And your expansion is due to temperature, your contraction is due to force. So again, delta P equals delta T. Delta force equals delta temperature. So now that you have that, just write out your equation, PL over AE for aluminum, PL over AE for steel, so on and so forth. Now, we're looking for stress. Why didn't I write sigma L over E? Well, that's because this is going to be, if I wrote sigma L over E, this would be sigma of aluminum over E, and this would be sigma of steel over E, which is different. So therefore, I'm going to have two unknowns in a single equation. Okay? So, you can still solve it. We're going to introduce another equation using summation of forces. Okay? But to make things easier, I'm just going to use PL over AE. Again, because P is equal. The amount of force you use to return your system to normal or to original position is the same. So P. So that's the reason why I didn't solve directly for stress. Okay? So still using PL over AE again, equals deformation due to temperature, alpha L change in T for aluminum, and then for steel. Plug in your value. So P is what we're looking for right now. Length of aluminum is given inches, 10. Let's see if it's uniform with our given. So our E is in PSI, so pounds per square inch. A is in inch squared, length is in inch, no problem there. Our temperature is in Fahrenheit, and Fahrenheit. So our final answer, no, our change in temperature is also in Fahrenheit, and 100 degrees Fahrenheit. Alright, so again, plug in your values. Again, length of aluminum 10, area 2, is 10 times 10 raised to 6. Again, uniform units, no need to convert. Plus PL 15 of steel, area of steel 1.5, E of steel is 29. Equals alpha of aluminum, so 12.8 times 10 raised to negative 6. So 12.8 times 10 raised to negative 6. Length of aluminum is 10 inches, so 10 times change in temperature, again, it was given, increases by 100. Therefore, that's already your change in temperature. That's not your final temperature. Increases by. If increases 2, then you have a final temperature. You need to know what's the initial temperature first. Okay, so take note of the wording of the problem as well. So increases by, so that's already your change in T, so 100. Plus alpha of steel, 6.5, length of steel, 15, so 15, and again, change in T is the same, 100. Solving for P, you get this value. 26,691.84. And then finally, to get the stress, remember the basic equation for stress is just force over area. And your steel and aluminum bar experiences the same force. So it's both P over A, P over A. P being the same, it's this. Then area of steel and aluminum are given 1.5 and 2 respectively. So 1.52. Then solving, you get these. Okay. Alright, that's your number 3. Any questions? None? Okay, do you understand number 3? Please answer yes or no. Okay, great. Next, number 4. Okay, there's no figure. At a temperature of 80 degrees Celsius, a steel tire 12 millimeters thick and 90 millimeters wide that is to be shrunk onto a locomotive driving wheel 2 meters in diameter just fits over the wheel, which is at a temperature of 25 degrees Celsius. So determine the contact pressure between the tire and wheel after the assembly cools to 25 degrees Celsius. Neglect the deformation of the wheel caused by the pressure of the tire. Then assume your alpha is 11.7 micrometer over meter degrees Celsius. Again, that's just 11.7 times 10 raised to negative 6 per degree Celsius. And then E is 200 GPa. Okay, so analyzing the problem, we're looking for pressure. So you have a tire, right? Your tire is at a higher temperature of 80. Then you're going to shrink that just over a wheel at a lower temperature of 25. And then your tire will cool down to a temperature of 25 as well. Okay? And because of that, because of its shrinking and fitting over a wheel, it's going to experience a contact pressure. And we're looking for what that contact pressure is. Okay, let's see the solution for that. So let's first write out the given initial temp 80. Steel tire 12 millimeters thick, so small t 12 millimeters. Let's zoom that in. Small t 12. Next, width of the tire is 90. Instead of using W, I use L because if you notice in our past lectures, this is the cross section of a tire, or rather of a cylinder, and your tire is just a cylinder, okay? And the width of your tire is this, which is denoted by L. That's why I use L, okay? Next, 2 meters in diameter. So the final diameter of your wheel will also be 2 meters. So that's your D 2 meters. Yeah. And then final temperature cools down to 25. So temperature of your wheel is 25, and then the final temp is also 25. Okay. And your alpha and your E. So how do we solve for that? Okay. So what's gonna happen there is, if you remember, this is equal to, or this is similar to a problem we've solved for before. Okay. Under strain number 3. So let's take a look at that again. The only difference here is that the final diameter for your tire is given. For us, it's not. We're given temperature. So if you look here, this equation, deformation equals PL over AE, obviously. Okay, and then here, our deformation is just literally change in that measurement. So we're going to change that. But let's see how we analyze that. So this is your tire, right? That's your wheel. your tire is gonna deform because of its shrinking. Okay, and it's gonna deform due to temperature. And that deformation due to temperature is being constrained by the presence of your wheel. Okay, so this is your wheel. Okay, again, you have a tire increased in temperature, then decreased in temperature. So it's gonna fit over your wheel. It's gonna experience the pressure. And your tire wants to deform further because of the lowering of temperature. But again, it's being blocked by the tire, by the pressure of your tire. So meaning, okay, the change in dimension of your tire due to temperature is equal to the change in the deformation of your tire due to pressure, or in short, force. So writing that in equation form. So deformation due to force or pressure, then deformation is equal to deformation due to temperature. Okay? Or since the final position of your tire plus wheel system doesn't change after tires fit snugly on your wheel, therefore total deformation should be 0. Okay? So meaning delta P plus delta T temperature equals 0. You can do this as well on your other equations. You can say, yeah, change in PAL, change in PST plus this equals 0, but you have to take note of your sign convention. For temperature, there's no problem because the sign convention for temperature will just show in your change in T. Okay, obviously, if the final temperature is higher, change in T would be positive, which means if the final temperature is higher, there's an increase in temperature, your object will expand. And remember, expansion is positive, contraction is negative. That's why you don't really need to think much about the sign convention of deformation due to temperature. But what you need, though, is here, for force. Same thing applies if it's contraction or compression, that's negative. Expansion or tension is positive. So if you're going to write this in this way, this should be negative sigma P. Why? Because as you can see, our forces are in compression. So negative change in P plus. Okay, so that's one way to write that, or write it this way. Here, if you remember thin-walled cylinder, the force due to pressure is T, right? Actually, it's F, but on your tire, that's gonna go out as T. The reaction would be tensile. So that's why positive. So positive delta P plus delta T equals 0. Okay? Even in our previous problems, this is tensile, therefore positive. Then I don't care about the sign of that. It's just gonna come out and change in T. Okay? Yep. So that's it. So that's another way of writing out your equation. So mind the sign convention of your deformation due to force. In expansion, positive, compression, negative, tension, positive. Right. So now, I'm gonna write this. So usually, as we know, it's PL over AE. But this is a tire. It's not expanding linearly, or it's not deforming linearly. As mentioned in our previous lecture, the change in dimension here is on its circumference, or radius, or diameter. That's why you have this equation. PL turns into P, again, force due to deformation on your tire. It's because of the tensile force reaction due to pressure. So that's T. Then the dimension L is replaced by the circumference of your circle, pi d. Then over TWE. TW area, cross-sectional area is this of your tire. So TW, usually for a rod that was pi over 4d squared, then usually cross-sectional area of your rod is given. So that's why that's just a value. But here it's not. You have to analyze what the cross-sectional area is, which is this. So thickness times width, then E. Okay, so that's why here it's T pi d over TWE. So T is your P, pi d is your L. Not really L, but that's a dimension that's changing. Then thickness times width is your A. And width is actually L. Let's just write that. Okay, then plus temperature, so alpha, not L anymore, because again the dimension that's changing here is not linear, it's circumference, so that's pi d. Then change in T. Okay. Then plug in your values. We're looking for T first, in order to find out what T is. So T, as you can see, pi d cancels out. Okay. Over TW, thickness is given 12, width is also given, which is your L, 90. Then E is 200 times 10 raised to 3. Everything in millimeter. Then GPA to Newton per millimeter, that's times 10 raised to 3. That's why this times 10 raised to 3. Then plus alpha 11.7 times 10 raised to negative 6. Again, we discussed why that turned like that. Times change in temperature. Final temp TF, initial temp AT. Final temp 25, initial temp AT. Equals 0. Again, it's equal to 0 because at this point, the movement of your tire, there's no movement for your tire. There's no additional deformation on your tire. Okay. Solving for T, you get this value. Then again, our goal is looking for pressure. Again, pressure is this. Okay? And because of that pressure, it experiences a force F. Okay, remember thin-walled cylinder, internal pressure. That's what we're looking for. Therefore, creating your equilibrium equation, right? Again, this is from thin-walled cylinder. There's a reaction here at the sides of your cylinder or of your tire, which is T. So creating an equilibrium equation, 2T equals F. Right? 2 to the right, 1 to the left, therefore 2T equals F. Or F equals 2T. And remember F, to get the equivalent force of a pressure diagram, that's just the area. So therefore, you have a pressure P here times area D times L. Okay? So PDL. Just similar to your bearing stress, right? We're gonna use projected area. So pressure times projected area to get the force. So here it's the same pressure times projected area, DL. Okay? So PDL equals 2T, and T is solved for. Therefore, solving for P, you get 1.54 MPa. So that's it for number 4. Do you have any questions for number 4? And feel free to ask any questions, okay? So if you don't have any questions, do you understand number 4? Please answer yes or no. Okay, good. Next. For the next part, let's solve it in real time. Okay. Number 5. A rigid horizontal bar of negligible mass is connected to two rods as shown in the figure. If the system is initially stress-free, calculate the temperature change that will cause a tensile stress of 90 MPa in the brass rod. Assume that both rods are subjected to the change in temperature. So again, first let's analyze. What are we looking for? Temperature change in T, that would cause a tensile stress of 90 MPa in the brass rod. Here. So for this to experience a tensile stress, there needs to be a force, a total force causing it to elongate. Okay? And if this is elongating, therefore your copper is shrinking. So again, for this to elongate, your copper needs to shrink. Therefore, for your copper to shrink, the change in temperature needs to be negative, or rather, we need a decrease in temperature for this to shrink. Okay? So again, copper will shrink, brass will elongate. And then, so that is our analysis. So to figure out by how much, let's try to draw a free body diagram first. Okay, so let me just copy this. Okay, so FBD. So I'll draw it there. So free body diagram, let's call this point A, right? So let's zoom in. Okay, let's call that point A, and then you're gonna have reactions at these rods, right? Bar. And remember, this is always would be in tension. So let's call this PBR, and this would be tension, so P copper, PCU. Then create an equation. So there's gonna be a reaction at A since this is spin, vertical reaction. So since I don't want to solve for that reaction, you can just take moment equals 0 at that support. Okay, so let's write summation of moment at A equals 0. So therefore, negative PCU, because counterclockwise. So negative PCU times distance from A, which is 3 meters. Okay. And then PB, sorry, this is clockwise rather, so positive, my bad, clockwise. PB, negative since counterclockwise, so minus PBR, PBR, for brass. PBR times distance, 3 plus 2, so that's 5, equals 0. And then, okay, so anything given, wala. So, there's going to be a tensile stress of 90 MPa in the brass rod. So, tensile stress is already given for your brass, 90. So, rewrite everything in terms of stress. Remember, stress is P over A, therefore P is stress A. So, stress CU, ACU times 3 minus stress BR, ABR times 5 equals 0. Plug in the given. Stress CU is not given, however, area of copper is given 1,500 millimeters squared. So 1,500, by the way, I did not convert 3 and 5 to millimeters because their units cancel out anyway. So for example, if I convert this to millimeters, this is times 1,000. This is also times 1000 equals 0. You can just divide everything by 1000 and you return to just 3 and 5. Okay? So I'm just keeping that 3 and 5. So rewriting this is now ACU 1500 times 3. So 3 minus runs is given 90 times area 1200 times 5. Then from this, I can solve for stress in your copper. Okay, computing for that. Can anyone solve since we have time? So please solve what is stress in copper. Correct, Julius. It's 120. Now what am I gonna do with that? Allah. Well, if you've seen the pattern or noticed, whenever we have something like this, we're most likely creating a diagram of their deformation. Okay? So now that I have that, next step is to draw or sketch the deformation. Okay, we've used equilibrium equation first. Okay, so again, our analysis is this will shrink, this will elongate, right? So that this experience a tensile stress 90. Okay? And then this will experience compressive stress. So drawing that, therefore, if this is tensile stress, this bar should move downward, right? Again, for this to experience tension. So if this bar moves downward, right, then this is what their deformation will look like. Okay? This will be the deformation of your brass bar. This will be the deformation of your copper bar. And remember, when you have a change in temperature, obviously your forces will react. So this is not only change in temperature, okay? Or deformation due to temperature. There's gonna be a deformation due to their reactions. And what will that look like? So let's start with your copper first. Okay. So this total deformation will be your deformation due to change in temperature. And then your bar will react. The tendency of your bar is to oppose that change in temperature. Therefore, if this is gonna shrink, right, the reaction at this end is to pull it upward. Okay. Therefore, the deformation being experienced by this will be lessened. Right? So that's minus. Also, since it's gonna be upward, okay, wait, it's gonna be a decrease. So that's gonna be deformation due to force. So P in copper in Cu. Okay. Same thing here. Her object now because of that elongation, because of that shrinkage, this bar will elongate downward, and again that's gonna be reacted on by your force. Okay. So all in all, this is experiencing a tensile force. Okay. So that's the greater deformation here. So that's deformation due to force. Again, because as stated in the problem, it's experiencing a tensile stress. So all in all, it's gonna deform due to tensile force as well. So tensile force, deformation due to force. Then, okay, because it's decrease in temperature, okay, that elongation will be decreased because your bar will compress due to change in temperature. Okay, so minus change in T of your brass. Okay, and then this is 3, and then this is 2. And as you can see, you get right triangles, and you can use ratio and proportion to create an equation, your compatibility equation out of that. Alright, so creating your compatibility equation. Let's use this triangle first. So that's delta T for copper minus delta force for copper. So this side over this side, so 3 equals this side for the larger triangle. So delta PBR minus delta T over total length 5. Okay. So again, the reason why here temperature ang nauna, here force ang nauna, because in the final position of this, okay, again, this will shrink, this will elongate and experience a tensile stress. Okay, so if this shrinks, therefore the change in temperature due to temperature is greater, right? Because you're experiencing a decrease in temperature, that's the one giving or making it shrink. Okay, and because of its reaction, it's gonna pull it upward, it's gonna elongate it. So that's why the elongation is decreased by the reaction of your copper rod. Again, because this shrinks. And this will elongate. And obviously temperature is not the one making it elongate because it's a decrease in temperature. So the one making this elongate is your force. So reaction force. That's why this is P. And then, since this is again a decrease in temperature, the tendency of your bar is to compress. So that elongation is decreased by that compression. That's why minus delta T. Yun. Okay? So figure out what's governing the movement of your object. So for copper, it's the temperature. For brass, it's the force. Okay? Now that you have that, plug in your values. So let's rewrite this. Let's multiply this by 5 and 3 just to eliminate the denominator. So this is now 5. Okay, and then since I'm given stress, or I've solved for stress and there's a given stress, deformation due to force will be sigma L over E, right? So this is now alpha L change in P minus sigma L over E. And this is all for copper. Then equals 3 times sigma L over E minus due to temperature alpha L change in T of brass. Okay, then plug in your values. Let's just move. I'm gonna move things around to make space. So 5. What is for copper? 16.8 micrometer over meter, so that's times 10 raised to 6, negative 6. And as you can see, L again cancels out. And change in T, that's what we're looking for. Change in T. Oh wait, no. Nope. Doesn't cancel out because length of copper is not the same as length of brass. Sorry. So length of copper 3 millimeters, so that's 3,000. Change in T. Okay. Then minus stress in copper is 120. Length of copper again is 3,000 over E of copper is 120. Okay. To MPa. That equals 3 times okay. Stress in brass is given 90. Length of brass 2 meters, so that's 2,000 millimeters. Then E of brass 100. Minus alpha of brass 18.7. Again, length is 2,000. And then change in T. Okay? Can anyone compute what's this change in T? No, malit. Malit lang yan. Sa tens lang. Okay. Oh, very good. Victor, John. 56.013 or just 56.01. Okay. So again, 56.01 degree Celsius, right? Okay. So there, that's number 5. Any questions with number 5? None. Okay. So do you understand number 5? Please answer yes or no. Okay, last problem for thermal stress. Right. As shown in the figure, there is a gap between the aluminum bar and the rigid slab that is supported by the two copper bars. At 10 degrees Celsius, that gap is 0.18 millimeters. Neglecting the mass of the slab, calculate the stress in each rod when the temperature in the assembly is increased to 95. Then for each copper bar, A, E, alpha are given as well as for aluminum. Okay, so what are we looking for? Stress in each rod when temperature is increased to 95. So there's a temperature increase, therefore all of this will expand. And then when this expands, there's going to be a reaction at your supports, constraining that expansion. Okay, so again, let's draw that. First, copy, paste, and let's write out our given. There. Okay, let's write the given first. So initial temp 10, then your gap is 18.18 meters, millimeters, or else final temp 95. Then, okay, for copper, area is 500 millimeters squared. E is 120 GPa. And then 16.8. And then for aluminum, okay, so it's micrometer per meter degrees Celsius. So I just wrote micro per degree. Okay. So to solve, let's figure out what happens when you expand this. Okay. So let's see. So just give me a while. I'm gonna have to draw this. Okay. Okay. Natagalan sa pag-drawing. Sorry. So, since we're almost out of time and I have to make announcements, I'm gonna upload the solution to this later instead. Okay. Medyo mahaba pa yung solution. Okay. So, again, sorry about that. I'm just gonna upload the solution. Okay. And then on Saturday, you're gonna have your seat work for thermal stress. And then, by the way, if you've noticed, I've already checked your modular exam as well as your quiz number 2 for module 2. So the final grade, okay. So the final grade that you see is your final grade, okay? Now, as a reminder, for module 1 as well, you can retake your modular, no, under the IP activities tab in your course, right? You have to retake the modular exam retake. Answer that. Keep answering that. I think there's unlimited attempts. Answer it until you get a passing score. Also, you can retake your assignment as well to help you achieve a passing score. So that's for module 1. For module 2, a number of you have a failing grade or have 69%. So if you want, bawiin nyo sa project, sa reviewer, you have until tomorrow to submit your reviewer to me, especially for those who have incomplete reviewers. Okay, so some of you only need to fix your reviewer to pass. Okay, again, submit your reviewer tomorrow by 11:59 p.m. Okay, to increase your grade for module 2. Then for module 3, right now, okay, obviously there won't be any more chances for completion for module 3. So make sure you submit all requirements for module 3 as well. Okay? And then, as a reminder, if you have 2 IP grades, you're gonna get a failing mark here. So 5 for 2 IP grades. Okay? So please try to check your grades at the grade center if you're gonna pass. And make sure to pass the requirements, fulfill the requirements and IP activities. Right? If you have any concerns regarding your IP, send me a course message. Okay? Yes, yung NG2, that's already your final grade for module 2. Yes, you're gonna have project 3 due on the 11th week. Okay, anything else? Do you have any other questions? Wala na. Okay. So again, Saturday seat work. Okay. I'm gonna make your seat work available at midnight on Saturday. Deadline of your seat work would be by the end of the day. So 11:59 p.m. on the same day. The next meeting next week, so next Saturday is your quiz number 3. And then we're gonna talk about torsion before that. Okay. So any questions, clarifications, concerns? Those who have IP grade concerns, send me a course message. I'll get back to you. Okay, Lana? Alright. Since you don't have any more questions, you may go. Goodbye, class.
Ma'am?
Yes.
Ma'am, kailan po ako pwedeng mag-take po ng modular exam
Okay.
2?
Kailan ka pwede?
Ay, yung sabi niyo po sa akin nung nag-usap po tayo mamayang 3 to 4:30 po.
Ano yun? 3 to 4:30. Remind me 10 minutes before your exam.
Kakonect po ako sa Zoom, ma'am, or ano po?
Yes, I'm gonna give you a Zoom link.
Okay po, ma'am. Sige po.
Ma'am,
Thank you.
Okay.
ma'am, paano po malalaman kung IP po sa module 2?
You can see it in your grade center. MG2. That's your modular grade already.
Oh. Ma'am, ilang percent po yung passing?
70.
70.
Yes.
Sige po, ma'am. Thank you. Magko-course message nyo lang po kung IP.
Okay. Sure.
Sige po, thank you.
Okay. Anything else? Wala sa stress. I'll upload the PDF file for thermal stress right after this. Okay. All right. Goodbye, class.